Now let's see theory of interference fringes. Now again we are going to do the same diagram. So what we have is we have two narrow slits, and then we have a huge screen right in front of it. Alright, so let's call this point as S1 and let this as S2. Okay, and this is the screen. Now again we are going to use some point here. Let's say some point P is present here. Now one more thing what we have to do here is the distance between the slit and the screen, we'll call it as capital D. Okay, this is a very important part. Anyway, so for now what we are going to do is we'll take this point P. From point P we'll take S1. So this is 1. Then again from S2 we'll have to consider this is one more. Alright, so S1P and S2P are the path differences that you guys already know. So there is one more thing. So now what we are doing is, see, from here we are going to take the center of the screen, meaning what we are considering here is this line is the center. Okay, so let's call this point as O. So O is the center. Now the distance between S1 and S2 we'll call it as small d. Capital D is between the slit and the screen. Small d is between the slits. Okay, so now what we'll do is from S1 we'll join the screen. Same way from S2 we'll join the screen. Okay, so let's call these 2 points as A and this point as B. Now every distance is measured from the center. So point P is at a distance of y from the center. Okay, so this is basically the diagram which is very important. Okay, now the path difference is nothing but S2P minus S1P, correct? So what we have is, we have x is equal to the path difference S2P minus S1P. Okay, so we have to look at this part. Okay, now for that S2P and S1P we are going to use the two triangles. Okay, so first triangle is S1AP, second triangle is S2BP. Okay, now first what we'll do is we'll consider triangle S2BP, that is in triangle S2BP, right angle triangle. So Pythagoras theorem. So we have S2P square is nothing but S2B square plus BP square, right? Okay, now if you look at the figure, S2B is nothing but capital D, correct? And BP is nothing but y plus d by 2, because S1 S2 distance is d, so OB will be d by 2. So we have this to be d square plus y plus d by 2 whole square. So this is S2P square. Similar way in triangle S1AP, S1P square is equal to S1A square plus AP square. See, again this is d square. Now AP will be y minus d by 2. So y minus d by 2 whole square. Okay, so what we got is this. Fine. Now we need to figure out S2P minus S1P, correct? Now for that what we'll do is we'll subtract these two. Okay, that is what we are doing is we are doing S2P square minus S1P square, because this is nothing but S2P plus S1P into S2P minus S1P. S2P minus S1P is nothing but X. Okay, so we get S2P plus S1P times X, which is the path difference, is equal to, okay, so here we have d square plus y plus d by 2 whole square minus d square minus y minus d by 2 whole square. So d square cancels. Now if you expand and simplify, we'll get this as 4y into d by 2. Okay, because a plus b whole square, right? So if you expand and if you simplify, you'll get this. So you'll get 2, so which is 2 times y into d. This is nothing but S2P plus S1P times X, correct? So X value will be 2yd divided by S2P plus S1P. This is what we got. Now in practice, P lies very close to the center. Okay, it will be like few millimeters apart. So S2P and S1P, we can approximate it to D. Okay, so what we are doing here, this part is very important. What we are doing is S2P is almost equal to S1P is almost equal to D. This is the approximation what we are doing. So now this formula will change to X is equal to 2 times YD divided by 2D, because both of them are D and D. These two cancels. So you will get X is equal to YD divided by D, correct? This is what we got. Okay, now we have to calculate what is the position of the maxima and what is the position of the minima. This part is very, very important. Okay, now for that, now remember what was the condition for a bright fringe. Bright fringe is basically a constructive interference, correct? For that, the path difference has to be n lambda, correct? Meaning x value should be n times lambda. Just now we got x value to be yd by d. So equate. So we have x is equal to, one is yd by d, another is n lambda. So we have yd by d is equal to n times lambda. In other words, we have y is equal to n lambda d divided by d. Meaning here n value is 0, 1, 2, dot dot dot. Meaning this gives us the position of the bright fringe. Any bright fringe. For the first bright fringe, put 0. The second one, put 1. Third, 4. Like this, whatever we have, we are going to get the value. Now, when I told put n is equal to 0 for the first one, what I meant was this for the central bright fringe, which is at O. Okay, so if you are considering the central one, then n is equal to 0. Then the first bright fringe from the central one, put n is equal to 1. Then second bright fringe from the central one, put n is equal to 2. Okay, so this is how it goes. Next, same thing for a dark fringe. So for that, we have x is equal to 2n plus 1 by 2 into lambda, correct? And here we got x value to be yd divided by d. So equate those two. So we have yd by d is equal to 2n plus 1 by 2 times lambda, or y value becomes 2n plus 1 into lambda d divided by 2d. So here also you can take the value of n to be 0, 1, 2, so on and so forth. Okay, so these things will give the position of the dark fringe. So we got for the bright fringe, we got for the dark fringe. Now very important point is fringe width, meaning what is the distance between the two fringes. Okay, two consecutive bright or two consecutive dark fringes. So for that, again we have to do a very, very small mathematical expression. Okay. Now see, for any bright fringe, we have yn to be n lambda d by d. Correct? So this is what we have. So let's say we have yn minus 1, meaning this is the n minus 1th bright fringe. This will be n minus 1 times lambda d by d, correct? So the difference, let's call beta to be yn minus yn minus 1. See, this will be n lambda d by d minus of n minus 1 into lambda d by d. So what do you get from this? So we will get beta to be lambda d divided by d, correct? So this is what we get. So this is basically the fringe width between two bright fringes. Let's try to do the same thing for the dark fringe. We'll see what it is. For that, we have yn (2n plus 1) into lambda d by 2d, correct? Then yn minus 1 will be 2 times n minus 1 plus 1 into lambda d divided by 2d. Again, we'll have to do beta. Beta is subtraction of these two, correct? See, if you take lambda d by 2d common, you'll get 2n plus 1 minus 2n. See, this is minus 2 plus 1. Minus 2 plus 1 is minus 1, correct? So plus 1, because minus of minus becomes plus. 2n cancels. 1 plus 1 is 2, and this 2 will get cancelled, correct? So what did you get? You're going to get the same thing. That is beta is equal to lambda d by d. So what can we conclude from this is whether it's consecutive bright fringes or consecutive dark fringes, the fringe width remains the same. So in every interference pattern, if you are using a monochromatic source of light, we get alternate dark and bright fringes, and all the fringes are of equal width. Okay, all the fringes are of equal width. So this plays a very, very important part. So this finally finishes Young's double slit experiment of interference.